Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, I think we can get started. It's my pleasure to introduce Jeff Foster from the University of Maryland. We go way back, shared an office at Berkeley. And so I'm happy to have him here today, and he's going to tell us about some new stuff, kind of different work than he's been doing in the past.
Okay, thanks a lot, Manuel, for having me here. So today I'm going to talk about a user interface we've been developing, which is something new for me to improve a static analysis. And this is joint work with my student Phang, Khoo, who's fantastic, and my colleague Mike Hicks, who's merely excellent. No, he's fantastic too. So I thought before I would do that, I would just give you a 50,000-foot overview of my research, so I could just advertise a few things that I won't have time to tell you about today. And if you're interested, you can go to my webpage for more information. So really, I have to say that software is amazingly good today, considering how complicated it is. Right? We've been working on software engineering for maybe 50 years, depending on how you count, and we routinely run software that's larger and more complex than anything you could have imagined, say, 20 years ago. Right? So that's great, but there's still a long way to go. And so this is the quote I always use for this. At least NIST estimates that a lack of software testing costs $20 to $60 billion a year for the U.S. So I don't know what it means, but we can at least all say software could still be a lot better. So my focus has been on developing new tools to help programmers build their software more easily, more reliably, and more securely. And my approach of choice has been static analysis, so analyzing program source code and really complementing testing where you look at individual runs and code auditing where you manually look over code. So static analysis is an interesting third approach that can automatically reason about the program, check limited but useful properties, sort of do the easy stuff, in some sense of easy automatically, and support the programmer in doing the hard stuff. And I've actually built a small pile of tools over the last several years. And these look sort of fairly disparate, but the overall theme is taking informal assumptions that programmers have that they've learned from being good software engineers and building systems, and then making them manifest in annotations or in inference systems and actually enforcing them. So today I'm going to tell you about path projection, which, as I said, is a user interface to try to make static analysis tools more useful. And that interface, we're actually going to use it for Locksmith, which is a data race detection tool for C that some of you may be familiar with if you know my student Polyvios Pradikakis. Yesterday at University of Washington, I talked about adding static typing to Ruby, which is a general-purpose scripting language. So that's pretty neat, I think. CMod is a system for adding modularity or for enforcing modularity in C. So .h files are interfaces, .c files are implementations. I looked at ownership and uniqueness, checking network protocol implementations, multilingual interfaces, and adding type qualifiers to C and Java. So anyhow, that's a very quick overview. And if you're interested in any of these, please go to the PL Group webpage at Maryland, and you'll find more. Okay, but let me start talking about today's subject, path projection. And so the motivation for this is, as you all know, there have been a lot of recent successes in static analysis for defect detection and prevention. And I mean, they've been fantastic. So Microsoft in particular built some really great tools and uses them internally to good effect. There are companies like Coverity and Fortify whose entire business model is selling static analysis tools. And there's been lots of progress in the research community on developing all kinds of new and interesting static analyses. But if you look at least the research literature, the major focus to date has been on static analysis algorithms. So it's been on building tools that are somehow precise enough for some sense of enough and still scale to large enough programs that they're interesting. And that's all great. I've done plenty of that. I think it's still important. But I think the other component that's equally important is understanding the user interaction with the tools. Because no static analysis tool is perfect, right? They can't be because of undecidability. And so there are two things that a user typically has to do with one of these. They have to triage bug reports, so they have to decide whether they're true or false positives. And then they actually have to fix the bugs, remediate them. And of course, if they don't fix the bugs, in some sense, we don't care about the static analysis at all. So successful static analysis tools are going to require cooperation between users and the tools. And an area I'm starting to do some work in is understanding how to build tools that are more sort of user-centered, that take the user into account in the algorithms that they have and in the interfaces that they used. And this project is a first step in this direction. It's a new user interface for existing tools. And the interface is to help users visualize code paths. So in the application I'm going to show you today, the code paths are call stacks. So those might also come up in, say, debugging applications. But we think the interface could also be used for control flow paths, data flow paths, program slices, and other similar things. Although we haven't actually tried it for those. It should be applicable. And the core principles of the interface are sort of inspired by, well, partially by principles of information visualization, which really asks how you can best explain something to users in a visual way, and sort of our experience based on several years of building and using these tools ourselves. So one principle is we want our visualization to be sort of true to the original source code. So we don't want to sort of take the original program and muck with it too much, or the programmer isn't going to recognize their own code, and it might be harder for them to understand and actually understand the output of the tool. And the other principle is we want to fit as much on one screen at a time as possible. So that seems like a really simple principle, but it's also really useful because if you constantly have to context switch by when you're scrolling things on the screen or jumping from one file to another, it becomes very hard to figure out what's going on in a large, complicated piece of code. So those are the two sort of guiding principles. And what we've done so far to try to achieve those is we have a prototype. It's more than a mock-up, but less than a full implementation of the interface. So it's built into a web browser. So it's implemented using WebKit. And I think for me, so I'm not normally a sort of user study guy. So for me, that's actually the most interesting thing. So we developed the interface based on observing users using the tool and finding out what worked for them and what didn't, and then sort of refining the interface iteratively. And then to try to validate that the interface is actually good, we did do a user study. And the task we asked people to perform was triaging Locksmith error reports. So not trying to actually fix the underlying bugs, since that adds a whole new level of complication, but just deciding whether a warning is a true or false positive. And we compared our interface to a standard viewer that's sort of similar to IDEs, or what you might expect in sort of a least common denominator IDE. And we found that path projection improved performance, and by that I mean completion time for this task. It had the same accuracy. So I don't know whether that's good, but it's certainly not bad that the accuracy didn't get any worse with it. And users liked it. At least when we asked them whether they liked it, they suggested that they did. So that's at least positive. Yeah.
How did you compare it to the standard IDs? Because they don't know how to display Locksmith bugs, right?
Yeah. So we made up. So what I didn't say. So that's the reason the standard viewer is in quotes, because we made up a standard viewer that does know about Locksmith error reports and is sort of representative of an IDE. One of the reasons we did that is we also didn't want to bias our study. If users had experience with one particular IDE and other users didn't, we didn't want to affect the study that way. So by giving them a least common denominator, we sort of even out the playing field. That's the theory.
Would the users pay for it?
Would the users? Maybe we should have asked that. Yeah, we didn't ask. I suspect our users were all undergraduate and graduate students. So yeah, probably not. Yeah. We actually had to pay them. So yeah. Okay, so I'm gonna give you a demo of the interfaces, and before I do, I'll just spend 2 slides talking about the actual static analysis underlying this, and you might have heard the same thing from Polybius a while ago. So Locksmith is based on essentially an alias analysis that's actually inspired by Manuel's work and Manuvir Das's and Jakob Rehof's. It's just an extension to that. So here's one very simple way to prevent races in your program. So you have a bunch of shared locations. Let's call them R. You have a bunch of locks L. And if you access a location R with lock L held, I'm going to say that R is correlated with L. So correlated is a bit of a weird term, but it matches a paper we published on the subject, so I'll stick to that. And then I'm going to say that this correlation is consistent if every time you access a shared location, you always use the same lock to guard it. And here I'm assuming there's only one lock, but of course you can generalize it to a set and then intersect them. And if there's always one lock that protects a shared location, then the program is race-free. Right? So it's not the only way to prevent data races, but it's an easy way. It's very common, and perhaps it's even what you should use if you don't have a good excuse to do something else. So one interesting thing about Locksmith is that it's context sensitive. So this doesn't really come up in the visualization I'm going to show you, but I might as well advertise it anyhow. So on the left here, we have a piece of C code that uses POSIX threads. So foo takes a lock and a location P, or a pointer to a location, acquires the lock, increments P, and then releases the lock. And then here we have two calls to the function where we first pass in L1 and X and L2 and Y in the second call. And I've labeled these so we can keep track of the two call sites. And Locksmith is a constraint-based analysis, so it does something like the following. It takes the variables in the program, it abstracts them into sort of nodes in the graph. So here we have X, Y, L1, L2, and P at L, so we notice that P is accessed while lock L is held. Of course, we have to figure that out, but I won't talk about that at all. And then we do a little bit of flow analysis. So we see at call site 1, X flows into P. I haven't even drawn an arrow here, so let's just pretend. L1 flows into L. And since X is P and L1 is L, and P is accessed when L is held, we can say that X is also accessed when L is held as well. And one feature of Locksmith, like I said, is context sensitivity. So we label these incoming flow edges with the call site, so we know that this location goes with that lock. So if we have the next call where L2 is passed in for the lock and Y is passed in for the location, we know that Y is correlated with L2, but we don't get confused and think X may have been accessed with L2. Because if we did that, we'd think there was an error, because X would sometimes be accessed with L2 and sometimes with L1. So it's context sensitive, which prevents that problem, and it seems to work well in practice. OK, so that's a very quick overview of the algorithm. Here's what happens when you run it. So this is an error message for an application I'm going to walk through well, not really walk through, but show you in a moment. And actually, I think these error messages are really good. So we worked pretty hard to make the errors sort of this easily understandable. And I should also clarify that this is actually not exactly the text that Locksmith will produce. It's a slight syntactic rearrangement of that text. So there's nothing here that Locksmith doesn't compute or show you. It just shows you in a slightly different form. So the way the error reports work is for every shared location, so up there the shared location is a global variable gcon_open, and there's the location of it. It reports the set of dereference sites in the program that may possibly race with each other. So in this case, for example, there's a dereference of that variable on line 601 of main, and there are no locks held at that program point. And there are actually 3 possible dereferences that we're interested in that may race with each other. And so, for example, this one here, main calls pthread create, which spawns a new thread, which calls except loop, which actually contains the dereference. So the pthread create calls go into the paths, and then down here main calls thread main, not thread main autospawn, but thread main, except loop, and that has the dereference in it. OK, so like I said, we worked hard to make these pretty understandable. So let's think about what you need to do to go through this error report and actually see whether it's a true or false positive. And there's basically 3 steps. And these steps are very particular to the way this analysis works, but you have similar things in other kinds of static analyses. So the first thing you need to do is make sure that Locksmith's alias analysis doesn't lead you astray. So you need to make sure that the accesses that it says are potentially racing are actually accessing the same memory location. All right? The second thing you need to make sure of is Locksmith might forget that a lock is held. So at a join point, if on one path the lock is held and on one path it's not, it will say, oops, the lock isn't held, and then go on from there. And that's actually safe in the sense of it will report more data races than it would otherwise because it will forget about locks. But it could result in a false warning. And then finally, you need to make sure that the accesses that Locksmith thinks could occur simultaneously actually can. And so the paths have to be realizable at the same time. And so that could happen if there are conditional statements in the program that would prevent the paths from occurring simultaneously. Yep.
So point 2, it wouldn't be a false positive if the other path actually could reach that point where the lock wasn't held. So what you're saying is that at some join point you forget it, but then there's like some branch correlation. And so you know that if you're at this spot, you came through that branch that held the lock.
Yeah, exactly right. I was thinking in particular of the example, if P, then acquire lock, do something, if P, release lock. That's perfectly fine, but we'll think there's a race in the middle because we will think the lock might not be held. So you're right.
So you don't do any branch correlation.
That's right. That's right. The only thing we do is if there's a call to try lock, we do know that on the true branch the lock is held and on the false branch it's not. Okay, so actually this is a pretty complicated task, right? There's actually a lot of things to do here. And in this particular study, we're focusing on this one right here, checking whether the two accesses can occur simultaneously. So in our experience, number 2 really isn't a problem in any of the programs we looked at. That doesn't mean it couldn't be a problem in the future, but it hasn't really come up. 1 can be a real problem. You tend to notice very quickly when aliasing is too conservative because you get this big blow up in the number of warnings and you get all these things aliased together and it looks like a mess. So you can usually see that's going on. Untangling it sometimes takes a little bit of work, and I'm going to defer that to future work. So there have been other approaches to showing alias analysis paths. So for example, the work I did in SQL or Cormac Flanagan's Mr. Spidey system looked at that as well. So we're just going to only focus on this part of the task, whether two accesses can occur simultaneously. So here is our mock-up standard viewer. And I'm going to, so I do know that the font is very small, and I'll zoom in on it a little bit later is this legible in the back of the room? It is. Oh, well, I don't have to zoom in. Excellent. So this is our standard viewer. And so the major pieces are, we've got a file viewer over here. And normally, in the experiment, we actually used a wide screen so that this wouldn't get cut off over here. But the projector is sort of narrow, so I can't do that. And this file viewer can be split vertically into multiple panes at the same time, so you can sort of see multiple files at once. Over here, we show the path, the error report. We call it the path report. And these things in blue are actual hyperlinks that will scroll this to the right place and highlight the appropriate line over there. So you could expect, if you were to integrate this into Eclipse, you could make some similar functionality fairly easily. We have basic searching capability, which you would expect in most IDEs. And then we have this checklist that I'm going to talk about later on. So OK, so that's the basic interface. And now what I'd like to try doing, and we'll see, demos are always dangerous. But let's look at what happens if we try to triage this particular error report. So I can go over here, and I can click on the dereference site. And I can see, OK, gcon open is accessed there. That looks pretty good. That's easy to understand. I don't see any locks around there. So I sort of believe Locksmith when it tells me nothing is held. So that looks pretty good. OK. Now I click on this dereference here. I'm actually in a different file now. Or maybe I'm not in a different file. I'm in a different place in the file. So we have gcon open here. And we can see that that is called inside of except loop. So that was the call. There's except loop up there. So the call was right there. And except loop itself was called in thread main autospawn. So that's there. And thread main autospawn was called in pthread create. And actually, if we're very good, we'll notice that pthread create call there forks the thread that accesses gcon open. And down here is the other call to gcon open from the first path. So it looks very suspicious that those two can happen simultaneously. We do have to look at the if statement that encloses the pthread create, and notice gspawn on demand has to be true, and then reason about whether that's actually possible. And then we can go look at the third one. We click on the dereference. That's also an except loop, so in fact we already saw that. And we say, OK, now that's being called in thread main. And if we step back from there, the pthread create is right there. And oh, actually, now I sort of see what's going on. That was the first pthread create. That was the second pthread create. So in either case, whether that's true or false, we're going to create one of those two threads, and they'll access the location. And then that will conflict with the subsequent access in main after the threads are created. So we have found a true data race. OK, any questions about that? Any complaints about the interface? OK. And by the way, so that's in a web browser. So Yid is amazing. He coded it all up in WebKit and JavaScript and stuff. So that actually wasn't that bad. I mean, like I said, we did a good job with the error report, but we can do a lot better. So understanding what was going on required tons of scrolling through the code. The hyperlinks were clearly helpful, but they were still kind of confusing because they cause you to sort of jump all over the program at the same time. So it's hard to keep track of the context as you're stepping through the path because you sort of need to keep it mentally. We need to compare multiple paths together at the same time, and that was a little hard to do there. And we needed to visually constantly switch between the error report and the display. And in fact, click on places in the error report, go to the display, and vice versa. So in path projection, in contrast, we try to make that process much, much easier. So here's the mock-up of the path projection display, and I've cut off the left here just to fit the more interesting center one on the screen. And the interesting things here are we still have the error report and the checklist. So these are invariant from one interface to another, and they're in fact hyperlinked in the same way. But now we're showing paths side by side. So for each one of these paths in the error report, we're going to display one thing in the window. And there's another one that's hidden by the scroll bar. Again, in the experiment, we used a widescreen display so that actually wouldn't be hidden. Zooming in, so sorry, I'm zooming into this little area on the screen there. You can see we've done two interesting things. So one is we've done code folding. So for every statement on the path, like gcon open that's interesting, we display that. And we display any lexical and control flow constructs enclosing that. So if there's a while loop or a function, or up here there's an if statement and so on. So we display just the lexically enclosing control flow constructs. And we also display them for other things like pthread create, and you can control the display of these other things. So we have a set of lines that are marked as interesting, and we display all the control flow constructs enclosing the interesting lines recursively. And then the other thing we do is we inline function calls at the call site. So here there's a call to accept loop, and we draw this little box, and we show the body of accept loop down there. Right? Oh, and I guess I didn't say earlier that we hide any lines that aren't interesting or lexically enclosing blocks. So clearly this is a lot shorter than if we showed the entire body of accept loop there. OK, so then so I just showed you this part of the interface. Now moving up to that corner, we allow multiple simultaneous searches that can be highlighted in a different color and controlled individually. And if you search for something, it will be automatically unfolded in the interface and highlighted. So for example, down here, a couple of occurrences of pthread create are actually shown because they're pre-selected in the search box. And you can also enter your own queries up there. All right, so let me do a demo of this and see what you think. OK, so here's the path projection display. And it takes a little while to load in because it's this amazing mass of JavaScript. But there it is. And it just expanded the multi-query search there on the fly. So on the left here, you can see we have the call to gcon open. And that's the only interesting thing sort of in the body of the while. So we just see the while loop. And we see the if g use timer there. Oh, I didn't even notice that before, right? Because I missed it since it was hard to see scrolling through the code. And you can see that happens right after the if then else up there inside of main. And in fact, we can sort of cheat because we already know the answer. We know that those two calls to pthread create are going to fork calls that will access gcon open and give us the data race. So we sort of already know, since we have advanced knowledge, that this will conflict with that. And it's all sort of displayed at once. Or if we go over here to the second line, then we can see we can actually justify that again. We see gcon open is in here, inside of a while loop, inside of accept loop, which is called in thread main autospawn, which was created by the pthread create. And then we can sort of, normally these would be side by side, but we can sort of scroll back and forth and notice that that's the same pthread create call we see up there, and then know that those two paths can happen at the same time, depending on the if. Rob, yeah.
So I don't quite understand what you're deciding to elide. For example, as you pointed out, one of the things I have to reason about is whether branches can be taken or not. And
yes.
Therefore, I have to know all the code that affects the predicate that's in the branch, right? So
that's right.
So is that elided or does it remain?
Yes, so it's elided. So by default, we elide only. So we show only the lines in the paths and the control flow constructs lexically enclosing them, and we do not look at the conditionals. So you have to look at them on your own. And you can do that in two different ways. So one is you can unfold the code if you want and look through it, and just figure out what's going on. Or you can use the search capability. So like, for example, down here, there's this end threads variable. And we might go over here, we might say, well, what's interesting about end threads? And then after a second, that code will be revealed. And yeah, you have to manually go through it and figure out what's going on with end threads. That's right. And I guess the other thing we don't do right now, so this doesn't come up in the code, but if you had a non-local control flow, so if you had a goto in one of these, then not just the lexically enclosing blocks would be interesting because you could sort of jump arbitrary places. And right now the interface doesn't show those. We could actually add that, and we're thinking about that. Jim. Yeah.
Sort of a simple version of program slicing.
It's extremely. I don't even want to call it program slicing because it's so simple. No. It's just. It's just a lexical. It's just a lexical traversal of the code. So really, really simple program slicing.
Is there some reason why you didn't do real program slicing?
So my understanding is that full program slicing tends to pull in lots and lots of the program if you're not careful. And there's like the approach to like Manu's Ritteran's thin slicing is pretty good, but we haven't looked at that. That might be one way to pull in more of the code in an incremental way. Sumit, did you have a question?
What do you do about aliasing here? There's some.
What about so there's actually no aliasing going on in this example. So we've eliminated that from consideration from the experiment. And in fact, we did some transformations on the programs. The particular benchmarks we chose had no aliasing issues in them for the particular warnings. So we sort of cheated a little bit by hiding that under the rug. Did you? Trish?
So how scalable is this UI? If I inline multiple levels, it's gonna, I don't know. What's your experience in terms of if I have a long error trace, how's that going to show up? Is it readable? What's the level at which this breaks down?
That's a good question. So let me see if I can. So I think this one might have a really deep one. So I don't know the answer to that. You can always buy a wider display, I suppose. But I think it will break down at some point, sure. And in fact, one thing we did originally was we inlined the boxes under the actual call site textually, like whatever the leftmost character of the call was, we inlined the box right there. And that really spread them out horizontally. And so all we wound up doing was trading vertical scrolling for horizontal scrolling. So here we do them much further to the left. And let me see, I might be wrong about this. Yeah, these examples right now, I don't have any really deep ones. And I don't know how deep you can go before it becomes unwieldy. It's a good question. Did you have a question, Matt?
I was wondering how the display you had before this compares to what Grammatech is doing, for instance.
For Grammatech, yes.
Because visually it's kind of in the surface of things it looks quite similar.
So we have a more detailed comparison in the write-up of this. So the Grammatech's, we think the Grammatech display is not nearly as good. So for example, the function inlining doesn't look as nice. They use colors in weird ways, in our opinions, that make it extremely hard to tell what's going on in the context. So I think they have a lot of the same features. In our opinion, we've implemented them in a better way. So that it's cleaner and easier to understand. Although the JavaScript is much, much slower than an actual C implementation. OK, any more questions about the interface?
This looks like a deeper false.
Oh, yeah, let's see. Well, it's still going, though. We'll give it just a couple seconds.
So the timeout is configurable.
It is, OK. Oh, OK, so here we go. There you go. That's a nice deep call stack. So we've got gcache hits, which is right there, which is called in cache get, which is called in get request entry, which is called in process client cache, which is called in process client, which is called in pthread create. And in fact, yeah. So I don't know, actually. That looks pretty good. So it worked. Excellent. And in fact, one thing you can say is how hard would this be to do without this interface? I mean, it would require quite a bit of context tracking. And in fact, I know this because I looked at a lot of these error reports myself manually before we had the interface, and it was pretty painful. Okay. All right. So, so in building the interface, we tried to use, yes?
Just one comment. So it seems like there are two tasks some kind of UI like this can do. One is like, validate whether this is really not a false positive or something like that.
Right.
And the other thing is like, okay, how do I debug this and fix it?
Yeah.
And it seems that those are two separate things.
Yeah.
You could presumably do completely different visualizations for each one. You could probably have a much simpler one which just says like, is this really a bug? And I don't want to spend too much time at that point, worrying about how I fix it. But I just want to quickly go over things and say, okay, this is real, and then go back and maybe use something like this when I actually want to fix it. Have you thought about that? Does that make sense?
Well, I think it makes sense. I think, though, that this particular interface is really it's the triaging interface. It's what it's what I did when we were writing the Locksmith paper, and I was trying to figure out whether the Locksmith error reports were actually real or not. Basically, I carried out exactly this task of stepping backwards from the dereference site, and so I don't see how you would how you make that any simpler. Maybe there's a way.
Maybe generating an abstract version of the concrete trace that would be easier to maybe look at.
I see.
And if the abstract one has the bug.
Right. Well, so one of our hypotheses is that, and this isn't something we really tested directly, is that programmers would prefer to see things just in their regular code form rather than in something that's been abstracted from the code. And the idea is just that it's their code, they're familiar with it. Programmers often think in terms of code, right, because they spend so much time writing it. So we really didn't want to draw a sort of boxes and arrows diagram. Although I think those things have their place. We didn't want to do it for this particular task here.
The sad thing is it's not their code, right? Especially in bigger projects. It's like, a very small part of that is your code. So.
Sure, that's true. I don't know. It would be an interesting thing to look at, to compare other, if we got away from this, whether there would be another interface that we could show. Okay, so we tried to use some principles of information visualization in designing this. So I thought I would just list them, just because I didn't know this stuff when we started this work, and I found it quite interesting. So one basic principle is to try to increase the user's memory and processing resources and reduce the search of information, and that's really what we focused on. So we folded away code, and we did this inlining to make important lines of code visible on the screen and put code lines that were related close together. Use visual representation to enhance pattern matching is another common principle. Here there's not that much of that, but we do use colors for the inline function boxes, and we use the standard old wonderful trick of using syntax coloring for the code, right? It really helps. And then encode information in a manipulable medium is also really useful, and we don't have too much of that here. Basically, they can fold and unfold cold and do search and highlighting on the fly. All right, so now let me tell you what happened when we actually did this experiment. And of course, we had to do the experiment twice because the first time it didn't really work. So we did a pilot study and we gained a whole bunch of insights, and then we fixed it and we reran the study again, and those are the results I'm going to tell you about today. So we compared the standard viewer to the path projection view. The task was triaging a Locksmith error report. The example I showed you was one of the examples that we asked people to look at. And we measured basically completion time for the task, qualitative feedback from the users, and we also observed user behavior, especially in the pilot study, and used that to fix some things for the subsequent one. So to give you some details, all the trials that we used were based on programs we used, we had applied Locksmith to before. So examples were like that. What I just showed you was the not web server. We had an FTP client and a few other things. Small programs, roughly 1,500 lines of code each, and they were not familiar to the participants. So they were sort of random C programs as far as they were concerned. In each experimental trial consisted of triaging exactly one warning. So that way we didn't. So we don't have anything in the interface about managing different warnings and keeping track of them over time or anything like this. So it's just triaging a single warning at a time. Like I said, there are no potential aliasing issues. So for these examples, all the shared variables in locks were globals. And that's just the way we picked the examples. And we did a bunch of semantics preserving simplifications based on our pilot study. So for example, some of our participants didn't know that static variables inside of C functions were global. So we just made them global so that they wouldn't get confused. We changed wait and signal to join. So that's going to break the semantics of the program, but it can preserve the race behavior. We got rid of dead code because of pound_if0 and similar things. And we simplified the code a bit. We converted some goto and switch statements to ifs to be a little bit simpler. So the design of the study was within subjects. And actually, our pilot study was between subjects. So initially in the pilot study, we had each user use only one interface, either path projection or the standard viewer. And then we tried to compare across users. And that really, really didn't work. And the reason it didn't work is because there's too much individual variation in the task. So some people are good at it, some people are bad at it. And so if you had some good people using the standard viewer and some bad people using path projection, that sort of swamps everything else. Here we have the same person first using path projection and then using the standard viewer, or vice versa. So people were randomly assigned to one of these two schedules. And that way, if there's one particularly good programmer or good data race debugger, then there will get a low score, low time for both standard and path projection, and the same with a bad participant. Yeah.
One person triages different bugs using the standard one and yours.
So I didn't say that quite yet. So we had the same set of tasks in the same order. So the same warning reports. So these are 1.2, 1.3, those are warning reports. So the same warning reports were done in the same order for everybody. And it's just a question of whether they got the warnings in the path projection viewer or the standard viewer initially. Does that make sense?
But what I'm confused about that, if they debug or triage a warning using one viewer, that gives, now they have more context the next time to see the same warning in a different viewer.
So they don't see the same warning. They do 6 trials, and each one has a different warning. The first 3 are these warnings, 1.1, 1.2, 1.3, and those are different warnings than these warnings over here. Okay. So they see different warnings each time.
Yeah, but there's still a problem. What if they see a really easy bug in one case and a really hard bug in the other? Okay, that may be averaged out by lots of trials and so on.
Yeah, where lots of is actually a small number. Yeah, but yeah, that's the idea.
So it seems like there's quite a lot of individual variation about reasoning about these kind of bugs, right? So did you get a measure of that, sort of how much individual variation there was between subjects?
That's a good question. Can we come back to that a little later? I have 2 answers to that. Okay. So so the pros. So first of all, this solves problems with individual variations. And it allows us to ask the participants what they think qualitatively of the 2 interfaces. So that's also good. The cons are, so there might be an ordering effect. So the users might decide the first interface they use is good, and they might not like the second one. Or maybe they're weird and they do it the other way, who knows. But there could be some effect there. And something that really did happen, a learning effect. So over time, users got actually much better at debugging data races, or at least much faster at it. And we actually did definitely see that in the experiments, and that's still present. We weren't able to eliminate it completely.
So in terms of learning effect, I mean, the other way you could have done it would be, rather than doing A, B, 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 right? You could have done A, B, A, B, A, B. Yes. So that the learning effect was more evenly spread out across the 2 conditions, right?
Yeah. That's a good idea. I guess the reason we didn't do that is because we felt that it actually takes a while to get familiar with the standard viewer and the path projection viewer. Yeah. I mean, ultimately, what would be great would be just keep doing more after this.
And all 6 tasks were on 6 completely different code bases?
No. So the answer is these 3 tasks were on one code base. These 3 were on another code base. They were chosen so they were in sort of different parts of the program, but not completely. So they were on the same. These 3 on one, these 3 on another.
And how many participants?
I'll get to that in a moment. 8, yeah. So the procedure, so we had an initial questionnaire with people's backgrounds and demographics, And in each session, they started off with tutorials on data races, Locksmith, using this checklist that I'll tell you about in a moment, and the interface. So we were really trying to damp down the learning effect, so we tried to give them as much information as possible before they started the trial. All right. And then they did one practice trial that we didn't time or anything, but they followed the standard procedure, and 3 measured trials. And in each trial, they were given the interface with a warning in it, and then they had to decide whether the warning was a true or false positive. We measured the time, and then after that, they did the same thing again, except they explained out loud what they were doing. And so there were 2 goals with that. One is to help them sort of learn themselves by explaining it, whether they had gotten the right answer or not, because we didn't want to tell them, because that might actually bias their results. They might start relying on us to give them the answers. And it also gives us some insights into their thought process. So for example, it helped us discover that static variables were confusing one of the participants because they explained it to us. All right, so let me talk a little bit more about the learning effect. So essentially, this happens because this is a really hard task, right? So triaging these bugs is hard. And the participants, they're all students. They're not professional programmers. They don't have lots of experience debugging data races. They hadn't used Locksmith, so actually that's not quite true. One of them had used Locksmith before. And really interestingly, they tended to get sidetracked while carrying out the task because they weren't quite sure what they needed to do to figure out what a data race was, even though they had these tutorials. So they tended to wander off and do things that weren't actually necessary. Like they did a lot of matching of lock acquires and releases. Even though you don't really need to do that to figure out whether it's a data race, you just need to see, okay, what locks are held along the path to here. You sort of only need to match up the release if you're trying to understand other things about the code. So what we wound up doing was not only giving them tutorials. Did you have a question?
Well, so with respect to that, so did they know that there weren't alias types of issues that would, because you were saying there were 3 different kinds of problems that Locksmith would have.
Yes. So I think the answer is, I don't know whether we told them, I'd have to check whether we told them directly that there was no aliasing, but everything in the error reports was just a global name. So it would have been, like it was pretty obvious because you'd go to the dereference site and it would say variable X, and X was a global. You can jump to the definition of it. So I don't know whether we informed them directly, but I doubt it would have even sort of occurred to them to worry about that in these programs. Okay, so what we wound up doing to try to help control the user's behavior here and get it so we could actually measure something is both tutorials, and we developed this checklist to help guide the user task. And actually, this turned out to be really, really interesting, and we didn't study it independently, but I think it deserves some study. So this is in the lower right corner of both interfaces, and it's the same checklist in both interfaces. So it's got a bunch of tabs here, and the user has to fill out each of these tabs, and then once it's done, they'll get a little check mark there, and then they click on submit over here when they're done, and when they click on submit, that ends the task. So that's their answer. And we start off with a little warm-up task that's shown on the screen, which is to just list the set of locks that are held and where they were actually acquired. So that doesn't usually take very much work in these experiments. You just have to do a little bit of scrolling. It's not a big deal. And it just makes sure that there's no strange things that happen with the first actual tab, which is here, path 1. So, and let me just tell you the result, or an anecdotal result that happened. When we gave people this checklist to guide them through the process, times improved dramatically. So in the pilot study, they took, in the final study, they took 41% less time than in the pilot study to triage the error reports, because they weren't doing all these weird things, basically. And I think it also probably helped cut down on individual variance, although I don't know that. Yeah.
Could you tell how much of that improvement was of the tasks at the beginning and the tasks at the end after they learned stuff?
That's a good question. Well, presumably we could. I don't have that data. I mean, we should have all the numbers to compute it, but I don't know. Okay, so let me show you the tabs and explain what's going on with this. So there are a bunch of tabs, and they just account for the different cases that can happen for determining whether paths are realizable, and they're a little bit customized to this particular experiment and to Locksmith as well. So the first case is if you have a dereference site, in the program, and there are no locks held when you do that dereference. And that dereference is in a thread that's created in a loop, like this example down here. So we have a dereference in a thread that's forked in a loop. Sorry, this is not really C code, but it's a weird pseudo-C. Then Locksmith will actually just report one path, because it just looks for syntactic paths through the program, and there's only one syntactic path sort of from main down to this call to P. So you have to check whether a dereference site is in a thread guarded by a loop, created in a loop, if there are no locks held. Right? If any lock was held here, it would never race with itself, so you could ignore it. But since if there are no locks held, you need to check. So we automatically look to see if there are locks held. If there are no locks held, we generate a tab for users to fill out. So for path I, you need to find out, is the thread created in a loop, where the loop count is greater than 1. And every tab ends with an out where they can say, are there some other reasons that the data race, that there's no data race? And if there is, then they explain them, and otherwise it's a data race. So they would start off up here, and they would have to choose yes or no for is the thread created in a loop. If they click on no, that's all they need to fill out. This tab is done. If they click on yes, then the next button is enabled, and they can look further and see whether there's any other reasoning in there. So questions are answered top to bottom. And then the next case is, going back to this display, so that was path 1, path 2, and path 3 on the display. And then there's the sort of more things that you'd expect, the pairs of dereference sites, and you have to check whether they may potentially race. And what you have to do for those is, well, there are two cases. First, you have to decide, is one of them a parent or an ancestor of the other one? That would be parent-child. Or is it some other relationship, which here we just called child-child for some reason. And if it's parent-child, you need to know, does the parent's dereference occur after the child is spawned? So Locksmith should check for that, but it might be wrong. So you need to see whether it's giving you a false positive. Is there a pthread join that would cause the parent to sync with the child? And this is something, so Locksmith doesn't account for joins. So we have to ask that question. And if not, there's a race, or unless there's some other reason. And otherwise, if we're in the child-child case, you just need to walk through the paths. That's basically the case we looked at before, seeing whether the children are mutually exclusive. So that was, for example, paths 2 and 3 that we looked for in the first example. So essentially, I think what's really interesting here is that this checklist is really the human component of the task. Right? It's the part that the automatic analysis falls down on, and we're trying to tell you exactly what it falls down on and what you have to check. And so I think that's actually pretty interesting and something to think about. And it actually took us a while to come up with the right checklist for this particular set of tasks. All right, let me get to the results. So there were 8 participants, 3 undergrads, 5 graduates. All of them had prior experience in C and multi-threading, although possibly not both. And we asked them to rate their experience in multi-threaded programming, and they rated a 3 to 4, where 5 was very experienced. And 2 of them had used, sorry? Undergraduates. 3 undergrads, yeah. Very experienced multi-threaded programmers, yes. And 2 of the participants had used Locksmith or Eraser. We used a widescreen monitor and Mac OS, and we disabled shortcuts just in case somebody knew about them. Here are the average results for all the participants. So this graph is a little bit confusing. So here's session 1, here's session 2, standard viewer on left, path prediction on the right. So one group is the left bar here and the right bar here, and the other group is the right bar here and the left bar here. So if you kept track of that, what happened was the group who used path projection first and the standard viewer second, they improved 55 seconds from session 1 to session 2. So pretty significant learning effect. And from standard viewer to path projection, they improved 188 seconds. And both of these trends were statistically significant. So like I said, there's still a learning effect here that's going on. And I wish we could have eliminated it, but that wasn't really possible. But notice that the improvement when you go from path projection to the standard viewer is sort of small, 1 minute. And when you go from the standard viewer to path projection, it's really big. So what we extract from this is that path projection is still really useful, and it does give you an improvement. Because when you add it it gives you a much bigger improvement on top of the learning effect. Okay. So here's some data about accuracy, and I have the detailed times here because that was the easiest way to present this. So the dots in red are one tab that was filled out incorrectly by a user, and these are the trials from left to right. So this one had 3 tabs, for example, and 2 users filled out 1 tab wrong, and so on. And if you count up all the dots, you can see that there's roughly the same number of errors, 10 for path projection and 9 for the standard viewer. And participants really screwed up in these 2. So there was 1 tab that was consistently wrong in both of those sessions. And what actually happened there is these were not perfect experiments. Not every task was completely isolated from the other. And both of these had paths that had a common subpart that was not realizable. And participants didn't realize that it wasn't realizable. And so they got that wrong. And we did not, I should also say, we did not try to account for wrong answers in the timing results. We just took the total time, no matter what the answers were, since I don't really know how to account for that, given that each of these was part of a sort of larger task that overlapped with it. And yeah.
So how did you go about picking the tasks? I mean, were they chosen to exercise different skills in terms of false positive finding and, that kind of thing, or is it just a smattering of tasks?
It was so I have a feeling it was somewhat ad hoc. So we had a set of programs that we had applied Locksmith to, so we understood what was going on in them. Some of those programs had problems with aliasing, so we eliminated those. We needed problems for practice problems and the tutorial examples, so that sucked up some of the corpus as well. And we sort of had some things left over, and we looked through the warnings for those, and we picked them as best we could.
So in some sense, they were chosen to be the least tricky instances of looking for races. So ones, for example, in which aliasing was not really a significant part of the race.
Yeah, I don't know if that's sort of least tricky, because I don't know whether, I mean, aliasing is not always tricky to figure out. It depends what the alias analysis does. Sometimes it's very obvious, sometimes it's extremely confusing. They were not ones that we chose that particularly, we didn't choose them to be particularly simple or particularly hard. Maybe what I should say is there were ones where filling out that checklist told you what was going on.
I guess really the gist of my question is, are there lessons to be learned in the mistakes that people made, despite the fact that you gave them a better UI,
right,
that could be used to improve the next generation of the UI and make more information salient to them?
I see. That's a good question. So I don't know the answer to that. What our current plans are is to try using the UI for some other tasks and see what happens. We think it's pretty good at this task, at least at the level we have it. So probably we would either, like I said, do other things besides Locksmith with it, or if we were to continue Locksmith, we would probably look at the aliasing problem and so on. So I don't have too many lessons to share with the current version of it. Did you have a question?
Is there a correlation between completion time and getting it correct? It seems like if you look at that 2.2, the one time it got correct, somebody actually spent a bunch of time to figure it out. And actually, that user 3, is quite thorough because look at 11 minutes on 2.1. But it seems like that's another effect that it has to be.
That's actually a very good point. So we did not look at that. One complicating factor, though, is that it's 1 tab out of 3, so they did the other ones right. We actually did. I think we gathered times in the individual tabs, but I think we decided that data was sort of unreliable because you might switch to another tab and it might inform your use of something you did previously. So I don't quite know how to tease that out. We could certainly see if there's a correlation between errors and time, though, overall. That would be interesting. Okay. This is sort of interesting. So we measured the mouse hover time over the Locksmith error report, the one that was hyperlinked. And the idea is that's sort of a proxy for where your attention is. And it's also a proxy for how much you need to sort of click on things over there. And we found that in path projection, you need to spend a lot less time with your mouse over the path report. And that makes sense because the path is sort of shown in the code. And remember, when I was walking through path projection, I didn't really even need to look at the path report at all. It was all pretty obvious in the code. So that's, I think that's a good sign. We asked for some opinions. So I'm sure these are highly trustworthy. So for each interface, we asked people to rate whether they were quick to learn, whether it was quick to learn, whether they were confident of their answer after using the interface, and whether they found it easy to triage the race or not. And so these are standard box and whisker diagrams with the median, the quartiles, and the min and max are the whiskers, and any outliers are dots over there. And actually, there's no statistically significant difference in the answers to these three questions. So they felt pretty good, I guess, about both interfaces, which was kind of interesting. Maybe that's because both interfaces are fine. Maybe it's a small sample. Maybe it was sort of limited exposure to both of them, so they weren't able to fully form an opinion. Perhaps the learning effect was still going on. I don't know. And then we also asked, do you prefer path projection to the standard viewer? And everyone but one user said that they did. So 7 out of 8. I should find out who that person is, right? That would be bad experimental procedure, so we won't do that. We paid everyone. Actually, the weirdest thing that happened, one user told us after the first session of the study, oh, I don't want to take your money because the experiment was too good. I don't know what that means, but anyhow, we forced the money on him in the second session. So then we also asked users to rate each feature of path projection. So the error report, the checklist, function inlining, code folding, the multi-query, and that the query reveals folded code on a scale of 1 to 5. And all of these answers are statistically significant compared to the neutral response of 3. Although, I don't know, maybe that's sensible because maybe they would like the features. Maybe they were not likely to say no. I'm not sure. One of the things I found surprising was that function inline and code folding were looked on very positively. So one user said code folding was the best feature. Another user said it was their favorite feature. And I actually expected this to be sort of controversial because I felt like anything we do that changes the code from the original view of it could be very confusing. But apparently people liked it.
Yeah. You started out by saying you don't want to change the code because programmers are familiar with the code, but these were, of course, not familiar with the code, right? So it wasn't their code.
Yeah, so maybe that's right. So maybe that's why we got that result. Absolutely. And then lastly, people did like the checklist. So like I said, we got that anecdotal improvement in time between the pilot study and the final study. And one participant said the checklist saved me from having to memorize rules. So that seemed good. 2 of the participants here and here didn't like the multi-query, or at least they didn't rate it favorably. But those users actually forgot that we had initialized multi-query with those 4 searches that were at the top in my examples. And so, maybe that's why they decided they didn't like it, because they forgot that they had actually used it. Okay, so I should also say what could be wrong with the experiment, although we've certainly poked a few holes in it already. So the most obvious thing, the results may not generalize. I mean, these are 8 students, not professional programmers, not experts on data races. So small population, small set of programs, as we talked about before. And the learning effect, is still there. It would be nice to be able to get rid of that. We did change the programs to make the tasks easier, right? I had that little list of transformations. And the task in the experiments is very focused. It didn't include aliasing. It didn't include looking for locks that were not held. And in general, doing those, understanding those, and understanding error reports in general could require a wider range of tasks that we don't directly support. And the standard viewer interface is certainly not production quality. So maybe if we gave somebody a real IDE and integrated the report in the right way, it would be better. Although that was a deliberate choice to avoid any potential bias. Yes.
So did you ask them how confident at the end of each task, how confident they were that they had the right answer?
So we didn't ask them at the end of each task. So we asked them what they thought at the end of the, with that particular interface, how confident they were overall. For each particular tab, or for each particular task, we asked them to explain their reasoning out loud after they had submitted their answer. So I don't have any anecdotal data for you about how confident they sounded. That would actually be interesting to find out. So yeah, I don't know.
At some level, in the end, with a test like this, it's up to the program to make a judgment call. This is a real bug, or this isn't a bug, and it's sort of related to the amount of time they're taking, right? If their job is on the line, and if they make the wrong call, they're going to be fired. Then they're going to spend a lot more time, and then the differences in the interfaces might actually show themselves, more strongly because So part of it, I think, is you have to capture that, or it'd be useful to capture that.
Yeah, that's a very good point. Yeah.
Another way of doing kind of a study is so the way I heard developers at Microsoft use static analysis tools is, typically prefix or prefast gives a huge list of bugs. And so they kind of have a two-pass thing. In pass one, I think they spend 1 or at most 2 minutes on each bug just to kind of triage it and say, is this real or not? And then the ones that they've marked as okay, they'll go and investigate further. So it'd be interesting to see a study where, you have a time limit and say you have this much time. And, basically, given this information and what you've seen, you kind of triage it, and then how many people get it right, and what's a reasonable time limit.
That's a pretty interesting idea. I would hesitate to do that before I was able to get rid of the learning effect. But once I got rid of that, that would be pretty neat.
The other way people set up these experiments is they reward people differently for getting the right answer and not getting the right answer. And some IRBs freak out about this and some don't. So I don't know what Maryland will do, but if you really want people to be careful and take their time and work till they get high confidence, you pay them more for getting the right answer and getting the wrong answer.
You don't shop that.
Wow.
You can't shop.
Not do negative reinforcement learning, positive reinforcement learning. For some IRBs. And some IRBs thinks that ruins their self-confidence and blah, 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 and you can't do it.
Those are the ones in California?
I don't know. Probably depends on how many the university's killed.
That's a great suggestion. All right. So, so that's the interface and the experiment that we have. So, I'm pretty excited by this. I really enjoyed doing this project, and I think it was a lot of fun. So the idea is a path projection. Fit everything on one screen. Try to follow information visualization principles, which means display paths side by side so you can see them all at once, and inline function calls and do code folding so as much fits vertically as possible as well. And then the results suggest that path prediction improves the times and that users like it. So that's good. I like that users enjoy the interface. And I think there's lots more exciting things to do here, like some of you have suggested. And we don't have the code available yet, but we have more pretty screenshots. So if you'd like, go to that webpage and take a look. So thanks a lot for your attention.
So at the beginning you said you're doing paths that are call stacks.
Yeah.
But then you said generalized to control flow and
Yeah, that's the
Do you really believe that?
Do I really believe that? So I think we can certainly get paths that are almost call stacks already in the interface. So this didn't come up in this experiment, but we have the ability to say, to pick out something. Well, I guess you saw it with multi-query. Pick out something that's not quite on the path and expand that as well. So I think that will work okay. For other kinds of paths, what am I doing? I'm sort of claiming more ground than I have a right to, right? So yes, I'm sure it won't work initially, and we'll have to come up with new ideas. But I don't know. I mean, I think
that's what I'm saying. The inlining doesn't work when the path also says it has a return aspect to it. It's not just a call.
Oh, I see. When you have more of a graph structure. Yeah, that's a good point. So yeah, so we can't display those. Is that true that we can't display them right now? So I think that actually, let's do a little experiment since I've got this up over here. let's pick like G spawn on demand. This will probably take a while, right? Well, no, that. Yeah, so it looks like right now I'm not seeing any new functions appear. No, see? Nope. Yeah, so I don't know how this interface would look if you had, I think it can have not just one sort of cascade of nested boxes, but can have several of them. But I don't know whether that would start to get too confusing or not. So that's a good question, Rob.
So I wanted to say two things about learning effect. Mm-hmm. So one is I think you're way too defensive about it. Learning effects are fine. Don't worry about it.
Okay, good. Thank you.
I mean, in the end, you're able to show that the difference in the effect, in the behavior that you're seeing, is not completely explained by learning effect.
Right.
It is explained mostly by the difference. And so that's fine. I mean, that's typically what you do, right?
Right.
The other thing about learning effect is that it tends to plateau after a while.
Mm-hmm.
So if you have enough warm-up exercises, if you have them do the task 3 times, 4 times, 5 times before they do it for real, then you don't see as much. So if you really did want to minimize it even more, you just have them do the trial tasks, do more of the trial tasks.
Yeah, I mean, the main reason we didn't do that is because the study was already, each session took 2 hours already.
Right.
And yeah.
That's at the high end.
Yeah.
It occurred to me that your errors were mostly in the last 2 tasks, and maybe people were tired by them.
Yeah, that could certainly be. Maybe they were just going through them and not caring about the result. That's possible.
More questions?